Hello everyone, my name is Bruno and I'm here to present you the work Constructal Design applied to a microchannel with two mounted trapezoidal blocks subject to laminar boiling flows. So my name is Bruno and I am a PhD student from FURG, which is the Federal University of Rio Grande. So our work will focus on microchannels, and microchannels, they consist of many small channels that together they form like a unique structure through each fluid flow, and usually it dissipates the heat that's being generated by some sort of system or some machine or equipment. And they are present in a lot of applications like heat exchangers in refrigeration systems, in electronics and microelectronics, in process industries, in power generation systems, and many other different applications. So here in figure 2, we have the computational domain of the problem that we proposed. We have here the inlet of the microchannel, which has a 0.1 of height and a length of 1.5 millimeters. Water enters the inlet here at the left side, and it passes through these two blocks here, and it exits the microchannel on the right-hand side here. And what happens is that both walls, the lower and the upper walls, they have a temperature of 573 Kelvin. So in that way, the water that enters the microchannel, it exits in liquid plus vapor state. So in our study, we'll be evaluating two different values for the mass flux. And these two values, they correspond to the Reynolds number of 0.1 and 10, which is well inside the laminar regime. So in our study, we applied the Constructal Design method for the geometrical evaluation of the microchannel. We'll be investigating the influence of the 8, which is age 11, and the higher width, L12 of the first block, over the heat transfer rate and the pressure drop. And this for different magnitudes of the ratio between the lower width, L11, and the higher width, L12 of the first block. The second block geometry will be kept constant. So in this study, we applied the mixture multi-phase model. The mixture is actually a simplified version of the Eulerian model. It has it calculates the conservation equations for the mixture of the phases. It has the equation of the volume fraction for the secondary phase, and it has also the difference between the mixture and the Eulerian model is that the mixture has algebraic expressions for the relative and the drift velocities. So here the three first equations are the conservation equations, the conservation of mass, momentum, and energy. It's pretty similar to a single phase problem, but the difference here is this M term. The M stands for the mixture. So I have the density of the mixture, the velocity of the mixture, the viscosity of the mixture. And here we also have the drift velocity, which is very important for the relative velocity between the phases, because we usually have very different velocities between the phases in this kind of problems. So to simulate the boiling process, we employed the Lee model. The Lee model is governed by the vapor's continuity equation, and it takes account of the heat transfer from both the evaporation and the condensation. It has these two terms here that are the rates of mass transfer due to evaporation and condensation. So depending on the temperature of the liquid or the vapor, we can have evaporation or condensation happening on the Lee model. So to perform the simulations in our study, we used the ANSYS Fluent software, the 18.1 version. We done a mesh independency study here in table 1. And we use the triangular volumes in our work, and we can see here that we applied some extra refinement closer to the walls. So to validate the model that we used, we compared our results with Vivekanand and Raju from 2015 in a very similar microchannel, only without the two blocks. And we can see that we had very good results compared to them. So the evaluation of the results was done in 3 steps. First, we have a thermal analysis, then a fluid dynamics analysis, and last we had a multi-objective analysis. So starting here with the thermal analysis, we can see that we have here the heat transfer rate for Reynolds 0.1 and Reynolds 10. And we can see the influence of the geometry on the heat transfer rate. We can see in here that we have a bigger difference on the geometry between these two ratios for Reynolds 10. Here we have the temperature and the vapor volume refraction fields. We can see here that here is the best thermal geometry and here is the worst thermal geometry. You can see that for the best geometry, you have a better heat transfer because of the higher height of the first block. Now the fluid dynamics analysis here. We have the pressure drop again for Reynolds 0.1 and Reynolds 10. We can see now that we have a much more pronounced difference between the cases. And also we can see that we have a very similar trend for Reynolds 0.1 and Reynolds 10. Here we have the velocity and the pressure fields for the best, and here below for the worst fluid dynamics case. We can see that the highest height of the first block causes a big obstruction on the flow, and this causes the pressure drop to increase quite a lot. Lastly, we have a multi-objective analysis, again for Reynolds 0.1 and Reynolds 10. We have here the pressure drop, and here we have the inverse of the heat transfer rate. We have the inverse because here the lowest value is the best, and here for the pressure drop, the lowest value is the best. So in that way, the geometry that's closest to the 0 point here is the best one. Here in this case is 0.1, and here again 0.1 is the best geometry for the multi-objective perspective. This geometry of 0.1 for both ratios is actually the same optimal geometry for the fluid dynamics perspective. So the important findings of this study is again what we just said, that the fluid dynamics have a much more influence over this problem in the conditions that we applied in this problem over than the heat transfer. So the highest height of the first block, it causes a stricture effect, and it significantly increases the pressure drop. So that is the major cause of the fluid dynamics having a much higher influence in the performance of the problem. And so this study, it highlighted the importance of having a multi-objective analysis, especially in a phase change problem, which was not previously investigated with the Constructal Design method. So for future works, we intend to study different geometries as well as different conditions like turbulent flow. We're already working on that. And we hope that in the next COBEM we can present you with these kinds of conditions. So we would like to thank you, the CNPK, the FAPERGS too, for this work. And we hope that you have enjoyed this presentation, and thank you.